Topic 3: Equilibrium in 3 dimensions, Part 3: Examples. Hello, students. Welcome back after the theoretical discussions about the equilibrium in 3 dimensions. Now it is time to explore 4 problems to understand how they are applied to the systems. I am Dr. Shushanta Chakraborty, Associate Professor, Department of Civil Engineering, IIT Kharagpur. The reference material is an worked out example from the Engineering Mechanics Statics, J.L. Merriam and L.G. Craig. Example 3.1, reference Merriam and Craig. This is a sample problem, 3 by 5. The uniform 7-meter steel shaft, this is a steel shaft, has a mass of 200 kg and is supported by a ball and socket joint at A. This is the ball and socket joint at A on the horizontal floor, and the ball in B rests against the smooth vertical walls as shown. Compute the forces exerted by the walls and the floor on the ends of the shaft. That is to be determined. So for this problem, we need to understand the characteristics of the support, that is the ball and socket joint at A, and also a, a ball type of thing just touching the wall, how the reactive forces will act onto this body or the mechanical system. Solution, step 1. If you have followed the lecture, theoretical lecture, then we have mentioned about the steps to be followed for solution of the problem. The first step is the identification of the body, which is the shaft here. The walls and the floor are actually the environment or the supports. From geometry, the height h of the point B above the floor can be calculated. You can easily do that. This height was not given. You can easily follow it from the geometry. Step 2, we have already identified the body which we want to explore, that is the shaft. Step 2 is to identify the forces and the moments which are active and reactive. Now, the only active force is the self weight of the shaft. So, the mass is given 200 kg. We can easily find out 200 into 9.81 is 1962 Newton, acting vertically downward from the center of gravity of the shaft, that is in the midpoint. The components of the reaction at B are the normal reactions by the walls on the shaft. Since the walls are smooth, no frictional forces which will be tangential to the wall will act. So it is only normal forces from the wall onto the shaft that will be working. And the components of reaction at A will be only force components without any moment, since the ball and socket joint does not provide any moment resistance. So now you can draw the free body diagram. You have the force components of the reaction at A and the force component at the reaction at B. You may observe that there is no BZ because there was no frictional forces. These are normal forces from the wall, and there is no friction, and the normal forces from this will be actually tangential to the wall, hence this does not exist. And from the midpoint of the shaft, the weight of this shaft will be downward acting. Now these are in equilibrium, and we need to determine, if this is known, the weight of the shaft is known, we need to determine all the forces. Please observe carefully that these forces, the line of action of these forces are at point A, and the line of action of these forces are meeting at point B. Apply equilibrium equations. So without thinking what will be most convenient or useful, I have written down the equilibrium equations straightforward. First, force equilibrium equations, and then moment equilibrium equations, and then see what happens. I think, students, you can make it out what we have done. I have accounted for all the forces acting in x direction, y direction, and z direction, and also all the moments acting around the axis. Now, the question is that what moment reference we will take. See, for us, since I have observed, I have a 6 unknown to be determined, and all these 3 components are meeting at this point, it is judicious for me to take the moment about a point, which is actually the point A, so that the moment created by these forces do not arise. So basically, I will be, if you can now recollect the relationship between the moment about the axis and the moment about a point, then you will recollect that the moment about the axis of the components, if you do the vector and then you take the components, you will get the moment about the axis. So you can easily calculate the moment about all the forces along the x-axis ax at A. So you can write down the scalar components of the vector equation like this. This you have to do a little bit of exercise. Like that, I can show you one. Suppose max is w into 3 minus by into 3. Please mind the sign. What according to the right-handed coordinate system, what rotation is positive and or negative, you know it is a right-handed system. So now go back, w into 3 minus by into 3. W into 3, so you need to have this distance halfway. W into 3, if you take the actually the moment about the x-axis, from this axis, it is located at 3 meters distance and it is trying to rotate this way. So you have this actually the w into 3 as positive. Now by into 3, the by tries to rotate it this way, the other way around, and the distance is actually, you can see the height of this from the x-axis parallel passing through point A. So you have a negative sign associated with it, and altogether this should be in equilibrium. So we have equated to 0, from which you can find out the different values if W is known. From the force equilibrium equations, readily you can find out the AZ, which is a vertical component of the reactive forces A, because that should be equated to W, because the system of reactions does not provide the resistance in vertical direction anywhere else. So now you can altogether, this is you can say that one of the moment equilibrium equation is no longer required because your problem is already solved. Anyway, I had played no trick. Simply, I had 3 plus 3, 6 equations. I have written down those. Later on, examined what is useful. In your examination, gradually with practice, you will also develop a feeling that where you need to stop. So I could have stopped it here, bx. All are solved. This, so I can now substitute back the values of bx and by into the first two equations, and I can get the values of ax and ay. So these are the values. Before actually, so my problem is solved, but let us actually look that can I have a vector treatment of this, because I have learned that, and very conveniently I can locate the vector. So I can see that moments, it is r cross f, and if I have the forces and if I define actually the, the distances, the position vectors from a point, then definitely I can express the moment with respect to the vector equations and in terms of ijk components directly. And that's what has been done next, just for your understanding. So you can define two position vectors, RAG and RAB. So it is the position vectors are here, RAG and RAB. Those will take care of this, the moment of this force and these two forces. Because if you are sitting here at the point A, the components AX, AY, and AZ will not bother you about any moment reaction. I am talking about the moment about A. So now you can express the equations vectorially also if you carefully define this position vector. Mind that these position vectors are from coordinates, so I have not explained, and you need to take care of that. And also the unit vectors are ijk. For simplicity, I have not put any overbar and others. So these are very much the unit vectors ijk. Now vector force equilibrium, instead of the scalar components earlier, it will be expressed with the vector form, and I hope you are well conversant with this ijk unit vector and this vector equation. So you can see immediately if this is a null vector, and if ijk are unit vector into three orthogonal directions, then there is no other way than to equate the coefficients to 0 if you want the null vector to exist. Similarly, so you can get the scalar components like before. Now you can also actually write down the vector force equilibrium equation MA about A with the help of the position vector RAB and RAG, but you need to do the cross product of the forces components Bxi and Byj I have written in vector form, and also the vertical force which is in k direction but in negative downward. The k axis is upward. The right-handed system, which when expanded, you expand this cross product and you will get this to be 0. You can write in determinant form, that's up to you. I am not giving all the details. Expanding further, you can easily come down to the scalar components of the equations and equating them to 0. As you know, the moment equation, it's a null vector, and the ijk unit vector orthogonal unit vector, you have no other option but to equate the scalar coefficients to be 0. And your solution looks much now like before, but you have applied it differently in vector form. The vector form actually relieved you from thinking that you cast it into vector form and forget about it. The manipulation will ultimately give the answers. But I will suggest that you also know that how to solve it by understanding the free body diagram and the static your scalar components. That will give much more insight. Also, with respect to this diagram, I can comment lastly that I have actually sensed correctly the direction of the reactive forces. But how will you know that unless you solve it? In complicated problems, the force components might be in the other directions. Don't worry, don't bother about that. You arbitrarily select them. If you are correct, the manipulation values will be actually positive, if not negative, to say you that you assumed in the opposite direction, nothing else, and everything else will be fine. So this much, the first example. We'll explore more of it later in the next video. Another 3 examples to come.